Okay, let's keep going. What is next? Let's look at the derivative of a constant. What's the derivative of f of x equals c? So if we apply the definition of the derivative right there, what would happen with a constant? We've never done something like this before. Well, clearly f of x would equal c, but what about f of x plus h? This would be c as well. There's no x to plug in. So for every x value, the y value is always that constant. So we would come to here, the limit as h goes to 0, c minus c over h. Well, c minus c is going to give us 0 over h, or 0. And the limit as h approaches 0 for 0 is simply 0. There you go. So the derivative, look at that, the derivative for any constant will always equal 0. Let's take a look at this graphically. I think it's helpful, kind of like how we did for f of x equals x to the first. So imagine the graph of, let's call it y equals c. Think of any point on that graph, could be anywhere. Well, what would the tangent line look like for any point on the line? The tangent line always moves in the same direction as the function. Usually if the function's curving, it's only gonna touch, like graze by at that one moment, at that one point. But if the function is a line, the tangent line is always moving in the same direction. The tangent line is just gonna be right on top of that original line. It is the same line. Of course, with the derivative, we think, well, what's the slope of that line? And in this case, you know, for a horizontal line, that would be 0. So it makes sense for any constant function, since the graph is a horizontal line, the derivative for any point is always equal to 0. We're going to call this the constant rule. D over dx of a constant c is equal to 0. It's kind of a nice one. Moving on to the constant multiple rule. Now, don't mix up the constant rule with the constant multiple rule. The constant multiple rule is when we are taking a constant and multiplying it with a function, c times f of x. In that case, when we do the derivative, the constant c will just carry along, and we multiply it by the derivative of the function f prime of x. I won't prove this one to you using the definition of the derivative. It would be pretty straightforward. All you'd have to do is factor the c out. And you could see, yeah, if your function is c, then in both terms in the numerator of the difference quotient, they both have a c. You could factor that out, and it would kind of come outside the whole thing, and there it is. It's, if you really wanted to see it, it's probably in the book, or you could easily look that up. Okay, or just take my word for it. If you've got a constant times a function, just carry that constant over, multiply it with the derivative of your function. Let's see this in an example, the derivative of 7x cubed. If we were to take the derivative of 7x cubed, the 7 is our constant multiple. So we could think of that 7 as almost like being pulled out of the derivative. So we only need to focus on the derivative of the x cubed. Well, we know from the power rule that the derivative of x cubed is 3x squared. So we've got 7 times 3x squared, which gives us a final answer here of 21x squared. Now, usually, I show you all these steps here, but when people do these problems, now that you've seen the rule, there's no need to show these middle steps. We can look at this and think, hey, The 3 multiplies down, it multiplies by the 7 to give 21, and then the exponent drops by 1, x squared. So no need to show this middle stuff now that we understand the constant multiple rule. The sum and difference rule. So the same rule will work if you're adding or subtracting functions, 2 functions together. So let's take a look at, here's the rule itself, the derivative of f of x, either plus or minus g of x. This is a really, really nice rule. It turns out if you're adding or subtracting 2 functions, you can do their derivatives separately and then add or subtract the results, just being consistent with what was happening before. So f prime of x, either plus or minus g prime of x. Okay, with these, we're all set to do full-on polynomials. Now that we know the power rule, the constant multiple rule, and the sum and difference rules, that's all we need for things like what you see right there. F of x equals 2x to the 7th minus 3x to the 4th plus x squared minus 5x plus 6. Let's do this derivative one at a time. And just like think about that polynomial. We're going to be able to get an answer without any other work, or, no other steps. We can just go straight to it. So let's think here. With the sum and difference rules, we can do these one at a time. So we'll start with 2x to the 7th. What is the derivative of 2x to the 7th? Well, multiply the 7 down, it drops by 1. F prime of x would equal, for that term, 14x to the 6th, right? Okay, now let's move to the next term. It's being subtracted. So we'll think 4 times 3, and then drop it, minus 12x to the 3rd. We'll keep going, plus x squared. Hey, we know the derivative of x squared. It's 2x, so plus 2x. How about minus 5x? Now this is interesting. The derivative of x is 1. So think of this like 5 times 1. And it would simply be minus 5. And finally, we have plus 6, but that's a constant. The derivative of the plus 6 is 0. So we probably wouldn't write anything. We just leave it like this. 14x to the 6th minus 12x to the 3rd plus 2x minus 5. There we go. Pretty powerful. I mean, imagine doing something like that with the definition, with the limit. Oh my gosh. No work at all. Boom, answer. Pretty sweet. Okay, let's try out this question on paper. Find all points x, y on this function, y equals 4/3 x to the 3rd minus 4x squared minus 12x plus 1, where the tangent line is, find all the points on that where the tangent line is parallel to y equals negative 12x plus 5. All right, I'm going to switch over here. It was y equals 4/3 x to the 3rd minus 4x squared minus 12x plus 1. We're finding the points where parallel to y equals negative 12x plus 5. Okay, so let's think. If we're trying to find where there are tangent lines parallel to this other line, what attribute of this other line do we really want to key in on and focus on? And it's the slope. We notice that this line has a slope of negative 12. We want lines that are parallel to that, so they need to have the same slope. We want to find x values where f prime of x is equal to -12. If we can find the x values where the derivative, which represents the slopes of tangent lines, where the derivative is equal to that same slope, then we know those tangent lines are going to be parallel to this other line. Okay, let's check it out. Now I called it f prime here, but y, let's call it the derivative y prime. What is y prime? Well, using our rules, let's see, 4/3 x to the third. The 3 multiplies and it cancels the other 3. So we have 4x squared minus, this would be 8x minus, that derivative is 12, and the derivative of the +1 is 0. Okay, so far so good. What we're going to do is set our derivative function equal to -12. What x values would cause our derivative to equal -12? And it turns out this is kind of nice because we have the -12 on both sides, so we could add 12 to both, right, equals 0. We could factor for x minus 2, and we'll end up with 2 answers. X equals 0 and x equals 2. Okay, doing pretty good. We found x values, but we want the full point, the full ordered pair. So we're going to take both these x values and we're going to find their corresponding y values. We can do that by plugging back in to the function. So for 0, if we plug 0 back in here, well, 0, 0, 0, that's just going to be y equals 1. So one of our points is 0, 1. 2, yeah, I'm not sure. Plugging 2 back in, let me grab a calculator. 4/3 times 2 to the third minus 4 times 2 squared minus 12 times 2 plus 1. As a fraction, that gives me -85/3. And so there's another point where the tangent line would be parallel to the line they told us, -12x plus 5. Okay, we gotta graph this. Let's see. So we're looking at y equals 4/3 x to the third minus 4x squared minus 12x plus 1. Okay, interesting. And we're looking for points where it's parallel to -12x plus 5. -12x plus 5 comes in really steep right there, right? Okay. And we just found the points. We didn't find the equations of the tangent line, but no big deal. Here was one of them at 0, 1. Okay, yeah, so that's a point on the curve. And yeah, I think I can imagine, you know, the tangent line is going to be parallel to that black line. It's going to come in real steep right through there. Yeah, that makes sense. And our other point was at 2, -85/3. Let's see, where is that? Down here. Okay, that blue point. So it looks like that tangent line would be coming along the back side of the purple and would come and just graze down here and keep going. Yeah, I can see that black line like sliding over a little bit, you know, right there, and that being parallel. We could find the equations of these tangent lines. We really wanted to, but I think visually, yeah, we can confirm that looks pretty good. Okay, very cool. Hey, let's stop this video here. We'll pick it up in the next one.